If you're going to play the game of quantitative consulting, there's no sense running away from it. You're going to have to work with data. Do you feel you have a good handle on what data actually is? I'm showing you a picture here. For the purposes of this course, we're going to think of data as being a collection of objects together with their attributes. We have an object, which is an apple, a specific apple, and it has 5 attributes. It has a shape, it has a color, it has a function, it has a location, and it has an owner. Do you all agree that this is an apple? Well, no, it's not actually an apple, right? It's a picture of an apple. It's a representation of the object that I have in mind, the apple. And in fact, it could be a picture of the very specific object that I have in mind. But it could also just be a random picture of an object that looks like an apple. And when it comes to the features, it's pretty straightforward. We just list or measure or record the actual feature. For instance, the shape is spherical, the color is red, the function is food, the location of that specific apple is in the fridge, and perhaps the owner is Jen. Right? Well, I'm going to have to ask you to think about this for a second. This is not a sphere. I dare say you've never actually seen an apple which was a sphere, or even vaguely spherical. The color, yeah, it's mostly red, and I think if I was asking you to think of an apple in your mind's eye, what you would see is something that is red or potentially green, but there's a fair amount of non-red bits on this picture. So there's a little bit of ambiguity there. But for the function, there's no ambiguity. We can all agree that the function of an apple is to be food. Well, for us, the function of an apple is food, but for the apple tree, that is not the function of the apple. The location, well, perhaps this apple is actually in the fridge, and the owner, if it makes sense to ascribe an owner to an apple, it could very well be Jen. In many instances, when we have features or attributes for objects, the measurement that we record for the attributes are at best approximate. Nobody would disagree with you if you were to tell them that the apple is spherical. It is. It's something like a sphere. And nobody would say, no, this apple isn't red. Yeah, it's red. Whenever we work with data, we try to represent an object or an observation with the help of a signature vector or a feature vector. In this instance, the attributes, also known as the fields or the variables, and the objects would be the instances, the rows, the cases. The feature vector, which is the specific collection of measurements of all the features for a given object, is meant again to represent the object. It's a finite representation of the object in data form. For the purposes of this course, data will come in tables, in objects that have their observations on rows and the measurements in the column. But that's not the only way in which you could store or represent data. One thing that could be useful to remember, though, is that the signature vector, the feature vector, is not the same thing as the object itself. It's a representation. You could have a data set that contains information about a bunch of people, and all the measurements you could take about a person might be there, but that doesn't actually constitute the whole person. It's just a representation of the person. Well, there's a very famous pedagogical dataset called the mushroom dataset, and it contains information about a number of mushroom specimens. Here we have the feature vector of Amanita muscaria, which is one of the mushrooms in the mushroom dataset. So I have its name, I have its habitat, woods, its gill size, narrow, its odor, none, and the color of its spores is white. I have more information about this mushroom. In fact, I have that information for all of the mushrooms. It's a feature on whether the mushroom is edible or poisonous. And there's nothing to see here. I mean, this is about as simple as things can get. Now here's a question for you. Do you think this mushroom, Amanita muscaria, is edible or poisonous? And you might be tempted to say, look, just look at this mushroom. It's obviously poisonous. But how do you know that? You do not know that because of anything that you see here. Woods narrow, none white. You need external information such as, well, this picture of the mushroom and some understanding of mushrooms and the color of their caps, perhaps, that gives you the indication that this is probably a poisonous mushroom. A few other things to notice. If I tell you that the habitat of the mushroom is woods, what does that actually mean? Does it mean that these specific mushrooms only grow in forested habitats? Is it sufficient that there would have been a wood there at some point in the near past? Can they live outside of the woods, close to the woods and the border areas? Gill size, narrow. What does that mean? Narrow as opposed to what? I don't know a lot about mushrooms. Presumably when they grow, they don't grow fully formed. They start being small and then they grow. Presumably the gills, which is what you find underneath the cap when you pull it up. Presumably the gills were at some point very, very small on account of the mushroom was small. The gills couldn't have been wide. How do you measure narrow and wide for gill sizes? Odor. Well, if I tell you this mushroom has no odor, what does that mean? Does it mean that when you take a sniff, when the mushroom is there or when it's not there, you sense no change through your nose? This is one instance where it's pretty clear. Presumably that's the definition of having no odor. Later we'll see that there's other potential feature values that this feature can have. And then you're wondering, like, well, how do I recognize some of these smells? Is it clear that everybody has the same sense of smell? The spores, the color, we have the same sort of note as we've seen before. Like, obviously here some of the spores are not fully white, but overall we would agree that these are white spores. Well, how do we answer a question such as, is Amanita muscaria edible or poisonous? Well, we could sort of build a model and sort of read off what the model says. So I'm going to take you through this model here and we'll make a prediction as to whether the mushroom should be edible or poisonous. Except, where's the model coming from? I just gave you a model. I explained nothing about how it was built, what data was used to build it. So it has to be some subset of the mushroom data set. Yes, but which one? You know nothing about this. You just see a model. And that's often the situation in which your clients will be when you go back to them with results. In this model, the first question you ask is what the odor of the mushroom is. If the odor had been musty, foul, pungent, spicy, and so forth, you would have concluded that the mushroom was poisonous, and if it had been almond and anise, you would have concluded that it's edible. Do you feel confident enough to be able to recognize a spicy odor as opposed to an anise odor? What does it mean to have a spicy odor? What's créosote? When the odor happens to be none, such as was the case with Amanita muscaria, it turns out that we do not have enough information to answer the question. We need to ask a subsequent question. Presumably what this is really saying is some of the mushrooms without an odor are edible, some of the mushrooms with an odor are poisonous. Ask further. But that also means presumably that all of the mushrooms that are musty are poisonous, and so forth, and all the mushrooms that have an almond odor, anise odor are edible. Otherwise, we would see for each of those a subsequent question to be asked. The next question to ask is what the spore color is. Well, we see, if you just look at the tree here, that all the mushrooms that have no odor but have green spores are poisonous. This model doesn't tell us how many such mushrooms exist, how many specimens, how many types of mushrooms are odorless with green spores. It just says that apparently all of them are poisonous. And all of them that have no odor but the following colors for their spores are edible. There is one, though, where we don't have enough information. So if a mushroom is odorless, and if it has white spores, we need to ask a subsequent question. We need to ask about its habitat. Odorless, white-spored mushrooms that grow in grasses, paths, and wastes, apparently, are edible. Those that grow in leaves or in woods are not. Is it the case? No, we just don't have enough information. Now, as it happens in the data set, there is another feature, the cap color. I did not include it in here because I just wanted to build a slightly different data set and decision tree to go along with it. But if the habitat had been leaves, in order for us to keep on using the model to make a decision, we would have had to have access to the cap color. And that's going to be a problem very often with data. Perhaps some model has been built in the past that it used a lot more features than the ones that are currently available to you. And we rely on past models. We have what's called the tyranny of past success. We rely on past models because they worked for us, but there's no guarantee that the data will keep on being maintained the way it's supposed to be maintained in order to be run through the models properly. There's a certain amount of maintenance of the data and of the models that needs to be taken care of in order to make sure that in the future you can keep on using the models that you've built with the data set that you're collecting. At any rate, this is not our current problem because the habitat was not leaves, the habitat was woods, right here. In which case, we still don't have enough information. Some of them are poisonous, some of them are edible. It appears that for odorless, white-spored mushrooms who grow in the woods, the deciding factor would be the gill size, whether they're narrow or broad. Narrow gill-sized, odorless, white-spored mushrooms who grow in the woods are poisonous, and if the gill size is broad, they're apparently edible. So our friend Amanita muscaria is poisonous. We're not surprised. We were expecting that to be the case just by the looks of it. But you're seeing here, at no point do we have the red cap appearing as a factor. It really sort of highlights the importance of being able to measure the narrowness of the gill size. What would it take for you to trust an edible prediction, by the way? Like, what if instead at the end of the day you went through this process and what you saw here was edible? Would you feel comfortable eating Amanita muscaria? Well, without knowing more about how the model was built, or how the data was collected, or what we mean by edible and poisonous, it's a little bit hard to trust the model, right? It could very well be that your data set is an aggregate of a bunch of specimens of a variety of types of mushrooms that have been, collected over the years. In which case, if you're saying that Amanita muscaria is poisonous, does it mean that it's poisonous for all, like every single Amanita muscaria specimen was poisonous? Is it saying that 90% of them were? Is it saying that 10% of them are? Do you know enough about mushrooms to know if this question even makes sense to ask? I don't know anything about mushrooms. I mean, I eat the criminy mushrooms that I purchase at the grocery store or that I get from the farm, but it's always the same mushroom. There I feel that they're always good for me, at least unlikely to be poisonous. But again, this is not information that's provided by the model or the data. This is external information. I suspect that if they were poisonous, they would get sued once they killed someone, the people who sell these mushrooms. There's another very crucial element here. Let me go back to the setup that is here for a second. What is the cost of making an error? What if Amanita muscaria had been edible, but the model tells me that it's poisonous? Well, the cost is I will miss out on eating a delicious mushroom. It's frustrating. Perhaps I really like mushrooms. I was really hungry. And then I don't get to eat it. Well, what's the cost of making an error the other way? What's the cost of having claimed that the mushroom was edible when it was in fact poisonous? The consequences are not the same. And this highlights something very important. In quantitative analysis and quantitative consulting, there isn't always going to be symmetry related to the cost of being wrong. In certain instances, if you're wrong, the worst that's happened for the company is they might have lost a few $1,000s. There's going to be other instances where if you're wrong, what's going to happen is literally they will be killing people. The product will be killing people. This is why it's so important to have domain expertise. You need to understand what the data set is really talking about before you go and throw it into learning models. By the way, this is a decision tree that was built with the mushroom data set, and if you've taken some machine learning courses before, you've seen how to grow one of those.